desperately contrast that with what's happening under this circumstance. Because in this circumstance, the center of mass of the object is changing location. There is no fixed pivot point. Technically, there's an instantaneous pivot point right here. But that pivot point only exists for an instant. And then the object has rolled a small amount, and there is a new pivot point. Meaning the pivot point is constantly changing, depending on how far the object has rolled down the ramp. So what was a pivot point at one moment, a new pivot point will exist a few moments later. Now, the other object as well, it had a center of mass that was changing height, but this object, its entire motion is predicated on the idea that the whole object changes from one location to another. So it will eventually make it to the bottom of the ramp. It did not have a fixed pivot point. So at no time was it being held in place. So this object does have both rotational kinetic energy and translational kinetic energy. We base the translational kinetic energy on the motion of the center of mass. And I know this seems like, why are you emphasizing it? Well, there's an important reason. And it might not be clear to most of you, and I don't think it will be for a while. But some of you this will click right away. And some of you will have difficulty understanding why I'm going to, from now on, write that this object has a velocity of the center of mass that is also related to omega. And I'm going to put a capital R here to remind us that there is a radius upon which this object is rolling. This R isn't just any point on the object. For an object that is rolling, we are using the outer radius upon which it moves. And I know some of you are like, why are you going over this like this? Because this is different. You think of a carousel. Carousel has a fixed rotational axis, and there's horses on it. You can sit on any of the horses you want, but every horse is going a different linear speed. You can calculate that speed by how far away they are from the axis of rotation. Does the carousel have translational kinetic energy? I probably wouldn't say it does. I'd probably say that all the objects on it are traveling at the same angular speed and have a single angular angular kinetic energy. But an object that rolls has its center of mass changing location and does not have a fixed pivot point. That's why I'm trying to emphasize it and why I want to make sure we understand that. A single point on the wheel, I gotta be honest, a single point on this wheel describes a very complex path. One that you are probably not ready to talk about because most of you don't know what a hyperbolic cosine is. Probably maybe 2, maybe not even that. Does your calculator have a whole second set of sine, cosine, and tangent buttons? They all do. All of your TIs do. If you look closely, you'll find them. And I'm not asking you to look closely and find them. But there will be hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. They are not trig functions. They are logarithmic functions. And it would be used to describe the path of a single point on this wheel, or could be. A single point on this wheel describes a weird path. Something like that. And this curvature is neither circular, nor parabolic, nor sinusoidal. It is hyperbolic. So you guys who are way interested in math, look up this one. It's interesting. Complicated to me. I have a difficult time understanding it. But you guys are smarter than I. You will likely understand it better. But if you try to think about how a single point on this wheel, anywhere on this wheel, actually moves, it can make your head hurt. Because they are complicated pathways. And at any moment, their actual physical tangential velocity is probably complex. Because they will have a velocity related to the fact that they are spinning and a velocity related to the fact that they are moving along with the center of mass. So for an object that is rolling, we will describe its velocity based on the location and speed of the center of mass only. I will never bring up anything else hardly at all. The only two locations of an object that I will bring up that I think are of value is that this point right here has a velocity of 0. It's touching the surface, and therefore it is not moving with respect to the surface. I'm sorry, you guys can't see that clearly because everybody's trying to maneuver their bodies, but that point has a velocity of 0. The center of mass would have a velocity equivalent to cm, or vcm. The whole thing has an angular velocity omega. And the very top, you might not believe this, you should prove it to yourself, has a velocity of 2 vcm. So at any one time, an object that's rolling has complicated subfeatures. I could not tell you how fast this piece is moving, nor how fast this piece is moving. But I bet it would be somewhat interesting. So for us, I want to just be very clear at the onset that when we talk about rolling, we tend to be talking about how the motion of the center of mass is moving, which is why in a problem like this, we would probably make comparisons between the gravitational potential energy the system has at the start and the combination of kinetic energies it has at any point beyond this. Now, the only difference between this conversation between first semester and second semester is that from now on, your energy calculation needs to be mindful of the possibility of two forms of kinetic energy. This is going to likely involve substitution. It doesn't have to, but without knowing the shape of the object, we're kind of at a dead standstill on what we could do next. Meaning, it's hard for us to figure out how this object behaves if we can't figure out how the inertia affects its motion. Which is why a lot of these problems will tell you the kind of shape you're dealing with, and then ask you, knowing what the shape is, how does the object perform when it rolls or moves through some kind of course? And we could do that here. We could say that this is a, pick your round object, there are 4, and let's stay away from the disk this time. Hollow sphere is 2/3 mr squared. The moment we know it's a hollow sphere, then we know information about its inertia. Clearly 2/3 of the mass seems to matter. Then begins the process of trying to figure out what we can ascertain. We could probably, knowing its moment of inertia, figure out how fast the object is traveling by the time it makes it to the bottom of the ramp. There's an adequate set of substitutions that will get us there. Things like plugging in the moment of inertia for I. This seems to make perfect sense. Why? Because we're going to have a common variable now to describe the inertia. We have m for mass. That 2/3 has told us how much of the mass matters. But it introduces yet another variable, r squared, which wasn't in there before. One way to deal with that is by recognizing its angular speed is related to its linear speed. So probably putting in v center of mass over r and squaring it. That will help us remove the radius, getting to the point where we're getting to the velocity of the object. Back to the kind of problem we did first semester. It is not a coincidence that the r cancels out. It's a feature. It's the fact that the radius has these properties. If the radius were bigger, how would it affect this? It would have more inertia, for one thing, but it being bigger means it doesn't have to roll as fast to make it to the bottom. It's bigger. And it happens to be at the same proportion. I don't think it's coincidental. I think it's the way it works. I think this increase in radius increases the inertia at the expense of not having to roll as fast to get to the same speed. So it's not, I think it's consequential. And that's going to equal mgh. The rest of this, that's on you. You guys can do algebra. And I don't really feel compelled to try every permutation of this. But unfortunately, I know that if I don't at least go one more step, I will have people who will be, well, you never did that in class. So 1/2 mv squared plus 1/2 times 2/3 mv squared equals mgh. I stop here on purpose to indicate clearly that the amount of energy we had before used to all go here, which is why our velocity for everything seemed to be the square root of 2gh all the time. But now, not now. We have more inertia in our system. There's the inertia of the center of mass, but there's also the inertia of rotation, which is going to cause our system to slow down. It doesn't lose energy. Same amount of energy exists here. It's just that it was hard to get the object to both move down the ramp and spin down the ramp. This is 1/2 and 1/3. When you add 1/2 and 1/3 together, what do you get? You want to try that again? Okay. Canceling out the m's, 1/2 plus 1/3 v squared gh. We will pause. There. Yeah, so you add those together, you get 5/6, which means that v is going to be equal to the square root of 6/5 gh. Now, clearly less than 2, right? You can clearly see that, I hope. The hollow sphere, if it rolls down the ramp, will be traveling slower than an object that slides without friction. Now, making that comparison is ludicrous because it's very difficult to actually get rid of friction. Very difficult. On the other hand, if you have something like these cars that have very light wheels and the wheels themselves have very little moment of inertia, they will probably make it down to the bottom of the ramp very close to the square root of 2gh. But if I grab a disc or a sphere or something like that, it won't. It's going to be much slower. And this is much slower. So we should expect that objects that roll are going to make it to their destination slower. This has a lot of impact. The thing that is valuable about this is we spent most of the first semester kind of negating the effects of friction as much as possible. Because in situations where we didn't have a constant angle or we didn't have the control over the system, it was difficult to gauge how much friction affected our problem because we couldn't always calculate the size of friction. We know that friction is very much related to the angle. Now, friction doesn't play a role that you think it does. There's friction acting on the object. The reason the object is slower is because the force down the ramp, mg sine theta, is being reduced by the friction up the ramp. That is still true. And the acceleration down the ramp is still based on those two forces acting on the object. The difference is that this friction in the past has been taking energy out of the system. That's not true now. Remember, before, the work done by friction was opposing the direction of motion. Therefore, that work was negative. We need to study how forces are acting here, and that's a more difficult discussion. But let's start with the overview. In this case, since this point, the point in contact, is not sliding with respect to the surface, this friction isn't doing negative work. Can't be. The point's not moving with respect to the frictional force. Therefore, negative work can't be done. In fact, we're going to find that the frictional force is doing positive work. Let's start fresh so we can talk about how a more difficult road for us. Dealing with force has always been something that we tried to leave out if we could. I'll remind you, if you're solving a problem using force, you are solving a problem using what is likely the most difficult way to solve the problem. For your notes, what might be easiest for this is for you to draw the circle in such a way that you can easily have arrows indicated on the circle. I also have choices about the way I present this. I can present this as if the object is pivoting about the center of mass, or I can present this as if the object is pivoting about the point in contact with the surface. It makes no difference to me which way I present it, but I will tell you that you should be able to understand both presentations. So my intention is to present different classes with different versions of this, and I will let third period decide. Do you want this presented as if the pivot point is located at the point of contact? This is option 1. Or do you want it presented as if the pivot point is at the center of mass? This is option 2. I am indifferent because I can do both of them. So raise your hand if you want option 1. Raise your hand if you want option 2. That is almost evenly split. Fantastic. So this class, I don't know. It's evenly split. I don't care. I got 3 classes to do this with. So I'm going to go option 1 in this class. And the reason is because option 1 is easier. You don't believe that at this point, but it is. So option 1, it will not change what you are to do next, which is to draw the 3 forces acting on the object. But do not draw them all on the center of mass. Please draw the forces at the location at which they act. For example, gravity acts at the center of mass. You need to draw the rest in there. All right, so that's all the time that it should have taken you. You only had to draw 2 more arrows. There is a normal force. And in drawing that normal force, be careful how you draw it. The normal force should be drawn in such a way that it is perpendicular to the surface and directed through the center of your object. If it's perpendicular to the surface, it acts along a diameter. And so the frictional force, do not be complacent here. The frictional force is situational. The only way to actually draw the frictional force is to know whether this is rolling up the ramp or down the ramp. And I didn't specify. So for this example, because I think it is probably more logical, let's assume that we are starting it near the top of the ramp and releasing it so that it is rolling down the ramp to match the problem we started with. Under that circumstance, the frictional force acts this way. So these are the 3 forces that act in our situation. I am not going to spend any time developing the net force relationships. I'm under the impression that we've already passed this unit. So I kind of feel like I can jump to this. You should be able to too. Those are all true statements. Any questions? If you had to think about these, then you should go review those notes before Monday. Here's the problem. In prior times when we've done this, we've kind of made this substitution. But I want to remind you that static friction is an inequality. And under the circumstances of rolling, it is very unlikely that you are coming anywhere near the maximum capacity of static friction. Static friction is almost always very small relative to the maximum amount of available friction, which means you will seldom ever be able to use these for a situation that is rolling. So do not, in any circumstance, believe you could probably start there at all. You'll be doing no substitution with those. You'll need more information because there's just too many unknowns here. And this is of no use to you, which means you have to consider torque. Now, in considering torque, I want to point out we're choosing a pivot point that is at the surface. And the reason why that's the easier pivot point is because two of the forces act at the surface, which means under the way I've drawn this right now, the normal force nor friction actually cause a torque. Do you see that clearly? So the only thing that's actually causing a torque is the weight of the object. Now, this is not how I think of it. I think of the friction as causing it to turn. I do. But this is a plausible way of describing it. And so we will use this as one of our descriptors. Unfortunately, net torque equals I alpha. And you'll notice we are not at the center of mass. So the first thing I want to point out is that I will have to use the parallel axis theorem. Not on the equation sheet, but I will have to use it. I'm also very likely to recognize that the angular acceleration and linear acceleration are related for the same reason that the angular velocity and linear velocity are related. But one good reason to use this method, one that I want to kind of throw out there now, is that this is the torque arm, and the weight is causing the torque, and this angle is just the angle of the ramp, which means that the calculation for torque is actually super easy. It's just R mg sine theta. Now, we are near the end of the class period. And what I want you to note is that I see a direct pathway to identify the acceleration of this system. Do you? I see this and this. And I'm pretty sure we can probably get rid of mg sine theta between them, solve for friction, or use this to solve for the acceleration. There are some things in here that we could probably cancel out. Some work to do. The problem is that I hope you're seeing it's very dependent on this. But also, if you haven't noticed or not, we can solve this relationship right away for the acceleration of the system. Right? We don't need another thing. The torque equation tells us it directly. That's one of the advantages of using the pivot point on the surface, is it's faster for getting the acceleration. It's slower for getting the size of the frictional force, but it's faster for getting the acceleration. I can do it right here. So if you look closely, I'm going to cancel out all the R's. Really? Nobody? Not one of you? Thank you. Go ahead. Tell me what I'm doing wrong. Yeah, I'm not. What I'm going to do is I'm going to write this as I over R squared. There's a purpose for that. And I'll kind of lightly say it because I'm going to get interrupted by the bell. What I want to derive here is kind of an equation for acceleration for anything that's round. I have 7 minutes? Oh, don't have time. So what I'm going to do is I'm going to divide out by R, but I'm going to put the R here. Are we okay with that so far? Now, you'll see why in a moment. So let's continue on. We want to solve for A. And I'm going to take my mg sine theta, put it in the numerator. Let's assume. What I have in the denominator is I over R squared plus M. Now, if this object weren't rolling, this would be 0. Right? If it was just sliding, that would be 0. And our acceleration would be g sine theta. because it's rolling, we have an extra term in the denominator. And this extra term brings together the amount of inertia associated with rolling. But please note, the top of this fraction is the net force on the system, mg sine theta. The bottom of this fraction is the total inertia of the system. And that equals the acceleration. This is still Newton's second law. And everything that rolls has a moment of inertia that has an r squared in it. So will r actually matter? Now, there's not a moment of inertia that doesn't have r squared in it. So what I hope you see here is that you now have the acceleration of any system where there's something rolling. If it's a ring, please notice that's the absolute largest this number can be. Thus, a ring has the slowest acceleration, right? Mr squared. In fact, if we put them in order, there's mr squared for the ring. There's 2/3 mr squared for the hollow sphere. There's 1/2 mr squared for a disk, and there's 2/5 mr squared for a solid sphere. It's that number out front. The bigger the number out front is, the bigger the denominator will be, the slower the object rolls. It's proven right there. Smaller that number is, the faster the object rolls. So solid sphere rolls the fastest. Ring, the slowest. And hopefully in your head you can figure out why they're in this order. Which one has the mass closest to the center? That's what all of those are trying to tell us. So the hollow sphere, a lot of the mass is on the outside edge, more so than a disk. The disk, more of the mass is towards the center. Solid sphere, most of the mass is near the center. Now, there's two more parts that should be done here. And one of them is to get an expression for the frictional force. You should do that. And it will be easier on you if we actually pick a shape in order to do that. So I will let you pick the shape. Ring. So if it's a ring, that just becomes m, right? Mr squared divided by r squared, the m's cancel. And all of this becomes a equals 1/2 g sine theta. Questions? If I want the frictional force, I'm going to use mg sine theta minus friction equals ma. So a little bit of algebra gives me 3/2 mg sine theta. Size of the frictional force. It should be 1/2. Thank you. Apparently I can't do algebra. That was just a solid mistake. 1/2 mg sine theta. So the size of the frictional force. Friction has to be less than or equal to mu mg cosine theta. We have found that the frictional force under this circumstance has to be 1/2 mg sine theta. Now, this is a condition. This is what's required. Understand the difference. Without this much friction, the system will not roll. It will slip. This is a condition of the surface. I'm telling you, this is what you have or you do not have rolling. This is what you have to work with. There's absolutely no reason why, given a condition, you couldn't determine if there's enough friction. Meaning, you could be asked if the coefficient of friction is mu, and they give you some number, will your object be able to roll? you would have to know this first in order to use this. All right. I know today was kind of tough. And I promise you it will be easier after this. The systems we started with, something like this. And the fact that if I have a system like this and under gravity, allow it to rotate under the torque provided by the weight of the object, then it will acquire some velocity as it begins to change height and rotate. It'll make it to a position like, say, here. And we'll have some velocity. Now, one thing that I want to remind you about is that the entire object has an angular velocity. Every piece of the object, being one whole specific object, has the same angular speed at every instant that it's moving. But different portions of the object have different linear velocities. So if you were riding along on this object, the linear velocity here would be greater than the linear velocity here. And I had called these tangential velocities. And we had said that the tangential velocity is proportional to how far away you are from the axis of rotation. And again, R shows up here, and R is everywhere. Ask folks in E&M, they are so tired of the letter R being so used for everything. It's like I was all over the place, and they have to keep track of all of it. Now, this R is a radius, for no better term, because these objects, this piece and this piece, are clearly traveling in circular paths, and the circle described by each object would have a radius equal to this distance. That's probably part of the reason R is used. But remember, this entire object has no translational velocity. The translational kinetic energy for this object would be considered 0 because there is a fixed pivot point that does not move with respect to the object. So although it has a rotational kinetic energy, it does not have a translational kinetic energy. And we showed early on in this conversation that a piece of the object has translational kinetic energy, but we could formulate a way of calculating kinetic energy based on the rotational speed, not the individual translational speeds. So, i.e., this object is considered to have one type of kinetic energy, and it is rotational. So that's how we ended up with this piece. And we did conservation of energy questions because the center of mass of the object did change height. And because of that, the gravitational potential energy was converted into rotational kinetic energy.